nature of nuclear force. Nature of nuclear force. So, what is meant by nature of nuclear force? So, first point, nuclear forces are charge independent. Nuclear forces are charge independent. First point, nuclear forces are charge independent. Charge independent. Nuclear forces are charge independent, and nuclear forces are very strong in nature. Very strong. Very strong. Then what is third point? Third point is short range. And fourth, nuclear forces have saturation property. That means they interact only with their immediate neighbors. So it has saturation property. That means they interact only with their immediate neighbors. Interact only with immediate neighbors. Okay. And nuclear forces are non-central forces. Nuclear forces are non-central forces. Nuclear forces are non-central forces, and they are spin dependent, angular momentum dependent. Spin dependent, angular momentum dependent. So, what is the characteristics of nuclear force? Nuclear force is charge independent, that is very strong, short range, saturation property, that means it interact only with immediate neighbors. Non-central forces, that is nuclear forces are non-central forces, and spin dependent and also angular dependent. So these are the characteristics of nuclear force. Okay, and we have to look about the decreasing order of magnitudes of strength of forces. So we know that nuclear force is a strong force. So that is nuclear force is a strong force. Nuclear force is a strong force. We have forces: strong force, Coulomb force, and weak force, gravitational force. So the strong nuclear force is taken as relative strength is 1. Relative strength is 1. Range of that force, that is 10 raised to minus 15 meter, because it is very small, and the range is inside the nucleus only, and the particles affected, that is hadrons, and the field particles, that is mesons. Particles affected and field particles. Okay, next force we know, that is Coulomb force. Coulomb force, another name is electromagnetic force. The relative strength, that is 10 raised to minus 2. So we know that nuclear force, strong force is strength is 1, and 1 by 100th of the nuclear strong force is that Coulomb force, and the range that is 0 to infinity, and the particles affected, charged particle, all particles are affected by Coulomb force. Field particles, that is photons. Okay, next force is weak force. Weak force relative strength is 10 raised to minus 11. This is also 10 raised to minus 15 is the range. Less than 10 raised to minus 15, that is weak force. That is between hadrons and leptons. And the field particles, that is vector field. Vector field. Next force, that is gravitational force. Gravitational force, and the range is 10 raised to minus 39. Sorry, the strength is 10 raised to minus 39. That is very strength is very small, and the range is 0 to infinity. We know that gravitational forces. So the particles affected, that is all bosons, and the field particles, that is gravitons. Graviton. So we know that the forces, nuclear strong force, relative strength is taken as 1, range is 10 raised to minus 15, hadrons are affected, field particles are mesons. Coulomb force or electromagnetic force, relative strength is 10 raised to minus 2, range is 0 to infinity, and all charged particles are affected, photons are the field particles. Weak force 10 raised to minus 11 is the relative strength, less than 10 raised to minus 15, hadrons are leptons are particles affected, field particles are vector field. Gravitational force is the weakest force, that is 10 raised to minus 39 is the 10 raised to minus 39 is the relative strength, and range is 0 to infinity, and the all bosons are affected, and gravitons are the field particles. Okay. So these are the things about the forces, and next we are going to study the Yukawa theory of nuclear forces. So what is meant by Yukawa theory of nuclear forces? Okay, so we can choose blue. Yukawa, the spelling is Yukawa. Yukawa theory of nuclear forces. So according to Yukawa, protons and neutrons have identical cores. They differ only in the meson cloud that surrounds them. Okay, according to Yukawa, protons and neutrons are identical cores. They differ only in the meson cloud. Meson cloud is the only difference. Only in meson cloud surrounds them. That is the difference in protons and neutrons. And these two interact with each other by the exchange of mesons. Okay. So second point, it is the interaction between protons and neutrons can happen by exchange. That is important. Exchange of mesons. They can interact. Okay. So how do that equations happening? So the theory, it is very important, the Yukawa theory. Protons and neutrons have identical cores. They differ only with that of meson cloud that surround them. They can interact by exchange of mesons. Okay. And what about the equation? Okay. What about the equation? The equation is proton changes to neutron plus pi plus. Okay. It is possible only inside the nucleus but not in free space. Okay. And also neutron can add up with the pi plus gives proton and neutron gives proton plus pi minus. Okay, and will gives to neutron. This type of reactions is possible between proton and neutron. Proton can interact with the neutron. Proton can emit as neutron plus pi plus, and then pi plus interact with the neutron will give you proton. Neutron changes to proton by emitting pi minus, and also it changes to neutron. This type of equations. So you understood? Proton emits neutron plus pi plus. Okay, neutron plus pi plus gives proton. Neutron gives p plus pi minus 1 gives neutron. Okay, this is the Yukawa theory of nuclear force. So you know that, you remember that theories. First, it is protons and neutrons are identical cause. They differ only in the meson cloud that surrounds them, and these two interact with each other by the exchange of mesons. P gives n plus pi plus, n plus pi plus gives p. Like that you have to remember the things. Okay. Next, we are going to study about the radioactivity. The radioactivity is the phenomenon of spontaneous decay of nucleus accompanied by the emission of alpha particles, beta particles or gamma rays. Okay, so the radioactivity is the phenomenon of spontaneous decay of nucleus. That phenomena is called as radioactivity, and it is accompanied by the emission of alpha, beta or gamma rays. Alpha, beta particles or gamma rays that are radioactivity. Okay, so you know the things. Okay, next we are going to discuss about the internal conversion. Okay, understood? Internal conversion. So what it means? Internal conversion is that an excited nucleus, instead of emitting gamma rays directly, transforms its excitation energy to one of the orbital electrons, and the orbital electron is ejected as conversion electron. Okay, so we know that the emission of gamma rays, okay, so by an excited nucleus, which emits gamma rays, we know that. But internal conversion means instead of emitting gamma rays, it transforms its excitation energy to the one of the orbital electrons. So we are considered as X, A, Z star is considered as an excited nucleus. We hope that it changes to XZA plus gamma. This is gamma emission. But here happens that we have to remove this. So here, but what happens in internal conversion, that is, instead of emitting gamma rays, it transforms its excitation energy to one of its orbital electrons. It transfers its excitation energy to one of its orbital electron. Okay, this orbital electron is converted. This orbital electron is ejected. This is called internal conversion. Okay, so the reaction is like this: XZA plus electron. So the electron is ejected. Okay, this is called as internal conversion. And what is next? Next we are going to study about internal pair production. Internal pair production. What is meant by internal pair production? If the excitation energy is greater than 1.02 MeV, the nucleus can de-excite by emitting directly an electron and positron pair in its own Coulomb field. That is called as internal pair production. The excitation energy greater than 1.02 MeV in this case, then the nucleus can de-excite by emitting directly an electron plus positron pair. Okay, so the nucleus can emit directly electron and positron pair for excitation energy is greater than 1.02 MeV. The nucleus can de-excite. The de-excitation is happening by emitting electron plus positron. This case is known as internal pair production. Okay. Next, we are going to, so the thing internal pair production, is it clear? The thing is, the excitation energy is greater than 1.02 MeV. Then the nucleus can de-excite by emitting electron plus, this is positron pair. This is called internal pair production. Next, we are studying about the beta decay. Okay, these things are very important in nuclear physics concepts. Okay, so what is meant by beta decay? Beta decay is the beta spectrum is found to be continuous spectrum, but the equation is very important. That is, we have to study about beta decay, negative beta decay, beta plus decay, beta minus decay and beta plus decay. That is, beta minus decay is that neutron changes to proton plus electron plus anti-neutrino. Okay, this is the beta negative decay. Beta negative decay means neutron changes to proton plus electron plus anti-neutrino, and beta plus decay means proton changes to neutron plus positron plus neutrino. Okay, so these things are called beta minus decay and beta plus decay. Okay, so in this we can see that the atomic number 1 increased by this beta minus decay. Electron emitted, atomic number is increased by 1. Here it is, atomic number is decreased by 1. Okay, but the mass number we can say that it is same. Okay, mass number it is same. The atomic number is increased by 1 here. Here it is, atomic number decreased by 1. This is the thing. But one more time you have to just remember the equation. you just write this equation. Beta minus decay means, just till up one more time you have to repeat the thing, that is neutron changes to proton plus electron plus antineutrino, and beta plus decay means proton changes to neutron plus positron plus neutrino. So you just by heart one equation, so you can write the another thing. Okay, beta particle, that is beta emission of beta particle. Emission of beta particle means it is Q positive greater than 0. Okay, so condition for spontaneous emission of beta particle, spontaneous emission of beta particle, it is Q greater than 0. Okay, beta particle can carry any amount of energy from 0 to Q. Okay, energy of beta can carry any amount of energy from 0 to Q. Okay, so that the thing about that. Thank you for watching and keep learning. Thank you.